Hello, everybody. Good morning, good afternoon, good evening, good night. Dear colleagues, let's start our seminar. Today, I have a pleasure to announce our speaker for today, our guest, Professor Peter Šemrl from the University of Ljubljana, Slovenia. He will speak on Wigner's theorem. Please, Professor, you can.
Thank you very much. I hope you can all hear me. So from my place, it's good evening to everybody. I hope my talk will not be a good night, will be just good evening mood. I'm going to speak on Wigner's theorem, which is a little bit, it's not entirely the main theme of your seminar, but things are simple enough. It's basically linear algebra, so it will be not difficult to follow. So H will always denote Hilbert space. Of course, this is something that people in operator theory and function analysis, they work all the time with Hilbert spaces. If you don't like Hilbert spaces, you can think of finite dimensional Hilbert space. It's just unitary space. If dimension H is n, then you can think of C to the power n, so n the space of complex n tuples ordered n tuples with the usual inner product, that's important. And then by this n is not the dimension of H. P sub n H, this is going to denote the set of all projections of rank n. When I say projection, I mean orthogonal projection. That means I'm speaking of self-adjoint idempotence. Means that we have that the underlying space, unitary space or Hilbert space, is the orthogonal sum of the image of this projection and the kernel, the null space of these projections. And image is of dimension n. If projection is of rank n, that means that the image is of dimension n. And of course, I can identify projection with its image. Projection onto onto some space, I can identify this space or with the projection. So I can speak of the set of all projections of rank n or the set of all n-dimensional subspaces. Of course, if I speak of the set of all n-dimensional subspaces, then actually I'm speaking of the Grassmann space. The Grassmann space of all n-dimensional subspaces. In the special case when n equals 1, then I have all projections of rank 1, so I'm speaking of a projective space. I will take the usual operator norm. So what is this? If we are in the finite dimensional space, then we can think of operators, we can think of matrices, and then we take the largest singular value. This is the usual norm. Or in the finite dimensional case, you can think of other norms as well, but we will take just the usual operator norm. Now, the Wigner's theorem is one of the most important theorem in quantum physics. And I don't know much about this background, but I know that when in the mathematical foundations of quantum mechanics, you have a certain experiment, and then you in quantum physics, and then you want to describe it mathematically. Then you take a Hilbert space, and the set of all projections of rank 1 is the set of pure states of this quantum system. This is the set of pure states. All states are all projections. Projections of rank 1 are pure states. And what is really important is the transition probability. Between pure states, this is probability that you go from one to the other pure states. Mathematically, transition probability between pure states is trace PQ. P and Q are projections of rank 1, no matter whether H is finite dimensional or infinite dimensional. These are two projections of rank 1. So everything is happening in the two-dimensional subspace. You take image of P, image of Q, and you take the linear span of those two images. This is a two-dimensional subspace. on the orthogonal complement, everything is 0. So you have here two 2x2 matrices. You calculate the trace of the product, and this is the transition probability between pure states. And this is what is important with the quantum system. Pure states and these transition probabilities, and Wigner's theorem describes what are all symmetries. You want to turn this quantum system somehow around without spoiling transition probabilities. So the description of symmetries, these are bijective maps on pure states which preserve the transition probability. And how can you turn, this is maybe not the right expression, how you can turn these things around without spoiling the transition probability? It is easy to guess with unitary operator, and that's the more or less that's the formulation of Wigner's theorem. So the theorem is the following. You have a bijective map on the set of all projections of rank 1. What is important, we have it here, transition probabilities are preserved. So if you have two pure states, P and Q, then the transition probability between the images is the same as the transition probability between P and Q. And then the conclusion is that such a transformation, bijective transformation on pure states that preserve transition probability, is implemented by a unitary operator. So we have this formula, phi p is equal to u p u star up, sorry, here for every p, not for every pq, for every p, for every projection of rank 1. A few comments, because I made a mistake intentionally. So if say if you have a projection P with of rank 1, so P is determined by its image is determined by a unit vector x, and this is again a projection of rank 1 whose image is ux. So this is exactly what we have here. We just turn around everything with a unitary operator. But look, we have to be careful. The conclusion is not that there exists a unitary operator such that this is true. There exists a unitary or anti-unitary operator. What is anti-unitary operator? Unitary operator is a linear map which preserves all the distances. Anti-unitary operator is exactly the same, just it is not linear, it is conjugate linear. It is conjugate linear. So these are the two possibilities. Now we can reformulate. This theorem, namely transition probability between P and Q is defined to be trace of the product PQ. How can you think of the if you have two projections of rank 1? Actually, what you have two subspaces of dimension. Two subspaces of dimension 1, and what is transition probability between them? Is trace PQ. It's easy to guess. This trace depends on the angle between those two subspaces, and also norm P minus Q again depends on the angle between these two spaces, and there must be a formula, and it's an elementary linear algebra exercise. This is an exercise on 2x2 matrices, because everything is happening on a two-dimensional subspace. There is a connection between, if you have two projections of rank 1, two one-dimensional subspaces, the norm P minus Q is the square root of 1 minus trace PQ. So preserving transition probability is exactly the same as preserving norm. So actually, we can reformulate Wigner's theorem in the following way. We have a bijective map on projections of rank 1. So we have a bijective map on a projective space over the Hilbert space, which is isometry, which preserves the distances, and then it is implemented by a unitary or anti-unitary operator. This is all very classical, all very old, and actually, I mean, this theorem, Wigner's theorem, which was formulated in two different ways. It can be also formulated with preserving angle between between one-dimensional subspace. It can be reformulated in several different ways, but this is a theorem which is extremely important in mathematical foundations of quantum mechanics, but from a mathematical point of view is actually rather easy. It follows almost directly from the fundamental theorem of projective geometry. From a mathematical point of view, it's easy, but it's extremely important in quantum mechanics. Now, because if we have such a theorem, then of course in mathematics, I do not understand that much about the background in mathematical physics, but in mathematics we always want to have the best possible versions. What does it mean, best possible versions of a theorem? We want to have weaker assumptions and still the same conclusion, something like that. And what could be the weaker assumption? So here we have a bijectivity assumption. Do we really need a bijectivity assumption to get this conclusion that the map is of this nice form, of a standard form? Whenever we'll have a map phi p equals u p u star, where u is a unitary or anti-unitary operator, I will just speak of standard maps. So can we get such a conclusion without assuming bijectivity? The answer is almost yes. Here, if I go back, so in Wigner's theorem, my first formulation, we have a bijective map which preserves all transition probabilities. So the next question, which is natural question, is can we do it better? We have a bijective map, but only a fixed transition probability is preserved. In particular, transition probability 0. What does it mean? What would be bijective maps preserving transition probability 0? These are bijective maps having the property that trace PQ is 0 if and only if trace phi P, phi Q is 0. But trace PQ is 0. This means exactly that the product PQ is 0. This is easy because P and Q are positive operators. What does it mean that the product PQ is 0? It means exactly that those two projections of rank 1 are orthogonal. Geometrically, their images, their one-dimensional images, are orthogonal subspaces. So can we prove the same? Can we get the same conclusion if we assume that only orthogonality is preserved? Perhaps in one direction only, not that P and Q are orthogonal if and only if P and phi Q are orthogonal, but maybe the weaker assumption, if P and Q are orthogonal, it follows that phi P and phi Q are orthogonal. Can we still get the same conclusion? What if we replace projections of rank 1 with, say, projections of rank 5? Do we still get the same conclusion? So we have a bijective map on projections of rank 5 on a Grassmann space of 5-dimensional subspaces, bijective map, which is an isometry. The second reformulation that I presented was that the map is isometry. Of course, we have operator norm. These are projections. So the distance between two subspaces is that you have two subspaces of dimension 5. You take the corresponding orthogonal projections P and Q, and the distance is norm P minus Q. And you have an isometry. Is it of a standard form? So these are questions that I'm going to speak of in the next half an hour, and perhaps I will have time to present some ideas. I hope I will present the connection with Gleason's theorem and maybe a little bit more. So the first question was bijectivity assumption. So look, what do I have here? I have a Hilbert space. Again, I have a map on the rank 1 projections, which preserves the transition probability. If you are careful, then you have noticed that before it's exactly the same as before, just here the bijectivity assumption is missing. There is no bijectivity assumption here. Do we get the same conclusion? The answer is yes and no. As you can see, we have a standard map. Just before, in the Wigner's theorem, the conclusion was that there exists a unitary or anti-unitary operator U. Here we get a linear or antilinear isometry. So in the finite dimensional case, linear or antilinear isometry is just unitary or anti-unitary operator. In the infinite dimensional case, you can squeeze the, you can have a linear isometry which squeeze the whole space into a infinite dimensional subspace. But I mean, the theorem is the same, just you have, in this case, you do not have symmetry between pure states of H and pure states of H, but you have a symmetry between pure space in a Hilbert space H and pure states in a smaller subspace K, for example. There have been, because this theorem is so important, there have been, in the literature, you can find many various proofs of this theorem. I believe the shortest proof that I'm aware of is the following one, is by Georgi Geher. It appeared in Physics Letters A in 2014. It's a very short, self-contained proof, not using anything, no other theorems. It's really short, really simple. And it is not a proof of the original Wigner's theorem, but is non-bijective version of Wigner's theorem. Now, the second question is, what if we preserve just one transition probability? And in particular, what if we preserve orthogonality? So what do we have? Like in Wigner's theorem, we have a map on projections of rank 1, which is bijective. Now, in Wigner's theorem, we preserved all the transition probabilities. Here we preserve just transition probability 0, which means that P and Q are orthogonal if and only if P and Q are orthogonal. Do we get the same conclusion? And the answer is yes. The map has to be standard. And those of you who know, when I was talking with people, I mean, I remember that as undergraduate and graduate student, I didn't know what was a fundamental theorem of projective geometry. I learned this only later. I was kind of surprised. This seems to me to be such an important theorem. But then, speaking about those things with other people, I learned that many mathematicians do not know what is a fundamental theorem of projective geometry. Okay, so maybe some of you know, maybe some of you do not know. Those who know fundamental theorem of projective geometry. So what we have here set of all projections of rank 1. This is just the projective space over a Hilbert space. We have a bijective map which preserves orthogonality. Two subspaces of dimension 1 are orthogonal if and only if the images are orthogonal. And those who know the fundamental theorem of projective geometry will immediately conclude from the fundamental theorem that phi has to be implemented by some semi-linear bijective map. And because it preserves orthogonality, it has to be unitary or anti-unitary. This is the only thing you have to do. So mathematically, Ulhoran's theorem is a far-reaching generalization of Wigner's theorem, because in Wigner's theorem, all transitions probability were preserved, here just orthogonality, but still from a mathematical point of view, it's just an almost direct consequence of a known theorem. In this theorem, bijectivity is essential. In Wigner's theorem, it is not, but here without bijectivity, in the infinite dimensional case, we have a lot of room to do strange things, and indeed we can do strange things if we do not assume bijectivity. And now this was transition probability 0. What if we preserve other transition probabilities? And this problem has been initiated quite long ago in a paper by Chik-Wong Lee, Lucian Plewnik, and myself. Some partial result was obtained there, and then it was pushed quite far by Georgi Geher in a paper that appeared in international mathematical research notices not that long ago, but now we have a final solution. This final solution has been obtained by Geher and Michiya Mori. And the solution is, by now, I guess those of you who who have been careful have already guessed what is the theorem. We have a bijective map. We have a fixed transition probability between 0 and 1, and this transition probability is preserved, and you get exactly what you expect. The map, such map, has to be of a standard form. As I said, this result is by Gehr and Mori, and will appear. It has been accepted in international mathematical research notices. For those of you who are interested, there are many references because these are classical theorem. I mentioned here just the recent ones, and if anybody is interested in these recent references, one can find many more from the past. Now here is a beautiful result, recent result that will by Pankov and Fitterlein. It will appear in Bulletin of London Math Society. It has been accepted for publication, but has not appeared yet. So what do we have now? We have a finite dimensional Hilbert space, and we have a map on projections of rank 1. And now we have this is really the optimal version of Wigner's theorem in the finite dimensional case. So what is Wigner's theorem? We have a bijective map. Here, as you can see, no bijectivity, no injectivity, no surjectivity, no regularity at all. You have just a map. In Wigner's theorem, it is assumed that all transition probabilities are preserved. In Ulhoran's theorem or in Gehr-Mori's theorem, only a fixed transition probability. Here, only transition probability 0 is preserved. And be careful. In Ulhoran's theorem, here you have if and only if, but here you have just we assume that orthogonality is preserved in one direction only. So if P and Q are orthogonal, then phi P and phi Q are orthogonal. In Ulhoran's theorem was bijectivity assumption, and here it was if and only if. So this is the optimal version. So we preserve just orthogonality and just in one direction, and no other assumption. I have to admit that I was thinking of this problem occasionally, every now and then in the past few years, and so I was very happy to see finally that this problem has been solved. And it was, of course, the result was not surprising. It was surprising that one can solve this problem. I mean, eventually it was clear to me that eventually I was almost sure that the theorem must be true, and we know it's true if we have a map on the finite dimensional on projections of rank 1 in the finite dimensional case, which preserves orthogonality in one direction only, then this map has to be of a standard form. So it will appear in, as I said, here are the authors. It will appear in Bulletin of London Math Society, and the proof was there were several things in several tools in this proof, including Gleason's theorem. And then I was thinking about this, and I came up with an alternative proof. It will appear in, so this is my proof of this theorem, and it will appear in Journal of Physics A. There are some other results, but for me this is the most important. This theorem, this optimal version of Wigner's theorem, we have just preserving orthogonality, just in one direction, no other assumptions, and the conclusion is that the map is standard. The assumption that H is finite dimensional, of course, is essential here. As I said, in the infinite dimensional case, we can do wild things. So this is a very nice theorem, and I will show you now that it can be deduced from Gleason's theorem. Gleason's theorem is another theorem, mathematically beautiful theorem, maybe not as important as Wigner's theorem, but still very, very important. One of the cornerstones in mathematical foundations of quantum mechanics, mathematically much, much deeper than Wigner's theorem. So this is what is the Gleason's theorem. I first have to explain what is COSP. I will call it COSP, complete orthonormal system of projections of rank 1, COSP. What is COSP? We have a system of projections of rank 1. They have to be orthogonal. They have to be orthogonal. Each two are orthogonal. And there is no rank 1 projection that is orthogonal to each of them. What does it mean? Because these are projections of rank 1, because they are projections of rank 1, you can, to each projection of rank 1, you can associate, of course, you can associate a unit vector in the image. Of course, there are this is not unique, because you can multiply it by a complex number of modulus 1. But to each projection, you can associate a unit vector in the image of rank 1, and this system of projections of rank 1 will be COSP if and only if these vectors will be a complete orthonormal system. I believe this is not that difficult to understand what it is. In the 5-dimensional space, you can take five one-dimensional subspaces that are each orthogonal, that every pair is orthogonal. And of course, this is COSP. I mean the corresponding projections for a COSP, a complete orthonormal system of projections of rank 1, because they're orthogonal, and of course you can, because you have a space of dimension 5, if you have 5 orthogonal directions, you cannot find the 6th one. Now, what is a density operator? This is something that is very important in quantum mechanics. This is a positive trace 1 operator. For us, H can be a finite dimensional space, so H can be, say, like 7-dimensional space. So what is a positive operator? Because we are speaking of, we have a 7-dimensional space, so we are speaking of 7 by 7 matrices. 7 by 7 matrices, positive operator, first of all, it has to be self-adjoint, a Hermitian. So if I am thinking of matrices, this is going to be a 7 by 7 Hermitian matrix. If it is a Hermitian matrix, then it is unitarily diagonalizable. In a certain orthonormal basis, it is diagonal. This operator can be represented by a diagonal matrix, and on a diagonal I have, because it is Hermitian, on diagonal I have eigenvalues. These eigenvalues are real. Positive means that those diagonal entries are no smaller than 0, are non-negative. Trace 1 operator means that if you sum up those diagonal entries, the sum is equal 1. So what are density operators? Up to unitary similarity. These are diagonal matrices. On diagonal you have non-negative entries, and the sum of those non-negative entries is 1. And of course, if you take such diagonal matrices and then you apply all possible unitary similarities, you get all density operators. Now, what is this famous theorem of Gleason? You take a map from projections of rank 1 to the interval 0, 1. So if you have such maps to interval 0, 1, that has to do something with probability, like a probability measure. And what is the assumption? The assumption, like these assumptions, like we are used to from probability theorem, from probability theory. If you have a complete orthonormal system of projections of rank 1 and you sum up their probabilities, you get 1. So of course you can then extend such map to all projections. So if you have a projection, say, of rank 3, this projection of rank 3 is a sum of 3 projections of rank 1, and you just sum up those probabilities, and in such a way you can extend this map to the set of all projections. It is well defined because of this property. It is easy to see it's well defined, and you have like in probability, if P and Q are orthogonal, then the probability of P plus Q is the probability of P plus probability of Q. So this is something that has to do with probability, and now the problem is that was the problem that Mackey was interested in. What are all such, let me call these probabilities, or I will say, what are all such Gleason's functions. And Mackey gave an example. If you take a density operator, then such a map, this is easy to see. Such a map is a Gleason's map. It has this property. What Gleason succeeded to prove is that these are all the maps, all Gleason's maps are of this form. Every, let me call this probability, every such probability is induced by a density operator. And that was, this is a highly non-trivial theorem. This theorem is much more difficult to be proved than Wigner's theorem. And therefore, it is not surprised that the optimal version of Wigner's theorem can be deduced from Gleason's theorem, which is mathematically much, much deeper. I was happy when I noticed this, and here is the idea, which is actually very simple. So what do we have? Let me go back to this theorem of Pankov and Wetterlein. So we have a map on projections of rank 1, preserving orthogonality in one direction only, and we have to prove that it is standard. And we have to prove that it is standard. How to do this? So phi is a map. This is a map on pure states, on projections of rank 1. And now, for every density operator, I define such a map phi sub d from pure states to interval 0 identity in the following way. So here I have this phi. This is my map from projections of rank 1 to projections of rank 1 that preserves orthogonality. And I want for this phi, I want to see that it is of a standard form. So for every density operator, I define this map phi sub d. And it is easy to see, because if you have a finite dimensional space and you have a complete orthonormal system of projections of rank 1, then by phi, such a cosp is mapped into some cosp, into some complete orthonormal system of projections of rank 1. Why? Because phi preserves orthogonality. And what does it mean that the system is cosp? If you are in 7-dimensional space, in the finite dimensional space, here we have finite dimensional space, the set of orthogonal projections is complete if and only if its cardinality is 7. In the 15, in the space of dimension 15, you have orthogonal system of projections of rank 1. Is it complete? Yes, if you have 15 of them. If you have less, then it is not complete. So cosp is mapped to cosp. So if P1, P2, say we are in 7-dimensional space, if P1, P2 up to P7 are a complete orthonormal system, then so are phi P1, phi P2 up to phi P7. And if you sum up those things, you get exactly trace of D. But trace of D equals 1. So Gleason's theorem can be applied. So this map, by Gleason's theorem, this map is implemented by some density operator. In other words, we started with this density operator, we defined this map, and this map is, we know by Gleason's theorem, is implemented by some other density operator. Let me call this operator E. That means that this map trace D phi P is implemented by E. So we have this equality for every projection of rank 1. And now what we do? Density operator, for this density operator D, I can take a very particular case. I take that D is equal to phi Q for some fixed projection of rank 1. Projection of rank 1, of course, has trace 1, is positive operator. So I can put in here, instead of D, phi Q, and I get that trace phi Q phi P is equal to trace E sub Q times P. Of course, this density operator E depends on this Q for every projection of rank 1. So I have the equality that trace phi Q phi, that for every let me repeat more precisely. For every projection Q of rank 1, I can find the density operator E sub Q such that trace phi Q phi P is equal to trace E sub Q P. And this is true for every projection of rank 1. This is just a straightforward application of Gleason's theorem. But now look, if I now put instead of P, if I put in Q, then I get here trace phi Q, phi Q. But phi Q is a projection of rank 1, trace of phi Q is equal to 1. So trace EQ, E sub Q times Q has to be 1. So what we have, this trace has to be 1. Q is a projection of rank 1, and this is a density operator. A little bit of linear algebra, very easy linear algebra. This can happen only if this density operator is equal to Q. E sub Q has to be Q. E sub Q has to be Q, because when you multiply a density operator with a projection of rank 1, the trace is below 1. It can be 1 only if this already takes all the, this is strictly smaller, except in the very special case that E sub Q is equal to Q. If one thinks just a little bit, this is an easy exercise. So EQ has to be equal Q. So what we have, the trace phi Q phi P is equal to trace, here it was E sub Q P, but actually here is Q. And this is true for every projection P of rank 1. Now, this projection Q was chosen arbitrarily, so this is true for every Q and every P, which means that my map phi preserves transition probabilities, and then I can apply Geher's short proof and see that, this map is of a standard form. So it is a self-contained proof, very short proof of theorem of Pankow and Fitterlein, but it depends on a very deep theorem. This is a theorem of Gleason. But the reduction to Gleason's theorem is easy, and then the conclusion is that if it preserves orthogonality, then it actually preserves all transition probabilities. This is where Gleason's helps, and in order to prove now that such a map phi is indeed standard, this is just application. Say if you want to do this in an elementary short way, you just use the proof of Geher, and you have a short proof of theorem of Pankow and Fitterlein. Now, the last question that I would like to address is if we take, instead of projections of rank 1, if we take projections of rank n in Wigner's theorem. So again, we have a map, bijective map, on the set of all projections of rank n, and we have isometry as before. So how can we, if we want to express these assumptions in a different way, we can say, because these are projections of rank n, these are, we can identify this with subspaces of dimension n. So we have a Grassmann space on a Hilbert space H, the Grassmann space consisting of all subspaces of dimension n, and we have a map on this Grassmann space. This map is bijective isometry. What is the conclusion? As you expected, it has to be of a standard form, except in a very special case. Let's say if you have subspaces of dimension 5 in 10-dimensional space, then of course you can send every projection into the orthogonal complement, and then you can apply unitary or anti-unitary similarity. Still, as you can imagine, this is still going to be an isometry, because taking a 5-dimensional, you have two 5-dimensional subspaces, and so the, let me say, the norm between those two, the distance between those two, is the same as the distance between their orthogonal complements. That is rather easy to see, and perhaps I have 5 minutes, slightly more than 5 minutes, maybe just some idea. So this theorem, there were 2 papers. The first one was by Botelho, Jamieson, and Molnar in Journal of Functional Analysis. It was a partial result. They initiated the study of this problem, and with Geher, we proved this theorem completely. We solved this problem completely, and I will present just a little bit of our idea. Now, what is the problem? Why this problem is much more difficult than the original Wigner's problem. So what is the problem? Assume that n equals 5. So we have 5-dimensional subspaces or projections of rank 5. So let us try to speak geometrically. We have two 5-dimensional subspaces. We have two 5-dimensional subspaces. And now how can I describe the mutual position of two 5-dimensional subspaces? If I have 1-dimensional subspaces, then I describe their mutual position by the angle between them. If I have 5-dimensional subspaces, then without going into details, I need 5 principal angles. What is the problem? The norm tells me just what is the largest principal angle. Does not tell anything about the other 4 principal angles. And that's the problem. For example, if P and Q are orthogonal, that means that the distance between them is 1. I know that the distance of P and phi Q is 1, but that means that there is one vector here and one vector in the first subspace and one vector in the second subspace, non-zero vectors, of course, that are orthogonal, but then the other principal angles can be smaller. The largest principal angle is the right angle, but the others might be smaller. And this is the problem, how to deal with this. So this is exactly the first step. You want to show that orthogonality is preserved. I mean, it's easier if you know that all principal angles are preserved. Then you know that mutual position is preserved. And then you can do somehow. But I mean, even the very special case that orthogonality is preserved is kind of, that was the most difficult step. And how we did this, let me describe this quickly. If I have to say, let me fix n equals 5. I have two projections of rank 5. I have two 5-dimensional spaces. And then I take the set of, let me call this midpoints. So these are all subspaces. All subspaces are of dimension 5, such that the distance to P is below 1 over square root of 2, and the distance to Q is below 1 of square root of 2. It's if the distance between P and Q is 1, then these numbers are very reasonable. I mean, geodesics in this space are not straight lines, so this is kind of reasonable. And now, so these are midpoints. And now let me explain. If P is a projection of rank 5, Q is a projection of rank 5. So assume that you have this simple, that you choose the appropriate orthonormal basis, so that you have for orthogonal projections P and Q, that you have this simplest possible matrix representation. Now I want to see what are those midpoints. What are those midpoints? And if you think a little bit, it's not that difficult. You start with 2 by 2 case, and then in 2 by 2 case, it's not that difficult, and then you go on, and you can somehow see that the set of midpoints is the set of all projections of rank 5 that are living in those upper 10 by 10 corner. You have 1/2 identity, 1/2 identity on the main diagonal. This off-diagonal elements is 1/2 unitary, and here is 1/2 unitary star. This unitary is 5 by 5 unitary operator. So these are midpoints. So as you can see, those midpoints, you can parameterize them with these unitary operators by a unitary group. Now, unitary group is a compact manifold. That's very well known. And we have an isometry. Isometry is a bijective map which is continuous in both directions. So compact manifolds are mapped in compact manifolds. And now we were able to prove that if P and Q are two subspaces of dimension 5, and the distance between them is 1, then they're orthogonal if and only if MPQ is a compact manifold. If they're orthogonal, then because of this, when I calculate this MPQ, I see that this is like a unitary group, so this is a compact manifold. And then this is not that easy to, not that difficult to guess, but a little bit, I mean, kind of annoying when you have to prove. If the distance between P and Q is 1, so you have the largest eigenvalues, the largest principal angle is right angle, but then you have smaller principal angles, and somehow you have to show that this destroys the structure of manifold. This is kind of you have to sit down and you have to work. It's especially for me that I'm not that familiar. I do not work in topology, so it was a little bit difficult, but it's a technical problem. So what you have, because you have a bijective isometry, compact manifold is mapped to compact manifold, so you know that orthogonality is preserved, and that's the starting point. And then you can somehow reduce everything to the Ulhorn's theorem. Of course, here there were subspaces of dimension 5. What if you take the subspaces of dimension infinity? So you are speaking of projections that are essentially infinite. Means that the image is infinite dimensional and the kernel is infinite dimensional, and you still get the same result. This is also a result of Georgi Geher and myself. So this is the theorem. You have an isometry on Grassmann space of all essentially infinite dimensional subspaces. This is an isometry, and again it has to be of a standard form. Here, of course, you can send first everything to the orthogonal complement, because orthogonal complement is again projection with infinite dimensional image and infinite dimensional kernel, and then you apply just unitary or anti-unitary similarity. If anybody is interested in this result, this appeared in Advances in mathematics not long ago. The idea was much more complicated than in the case of finite dimensional subspaces. We somehow had to analyze geodesics between P and Q, which are orthogonal, and my time is more. I guess my time is over, so it's better to stop here. The idea is somehow, let me just maybe that's just 1 minute. You take two such projections.
You can speak more. Go ahead.
Yeah, I will speak just 1 or 2 minutes. You take two projections, P and Q. Both of them have infinite dimensional image and infinite dimensional range. And then you have midpoints. Now, the problem is, again, if norm P minus Q is 1, that does not mean that they're orthogonal. Mean that in this guy, that the supremum of angles between vectors from P and Q is the right angle. The supremum, it's not even clear that it is attained, because we have now this problem with infinite dimensionality. But okay, let's say we have kind of a right angle, but these other angles can be smaller. Now what to do? We are considering again the midpoints, the points that are a distance 1 over square root 2 to P and to Q. And then we do not have differential structure, so we can define somehow what is a geodesic. What is a geodesic? I will show you what is a geodesic. We define all the distances between all those points on the geodesic, and if P and Q are orthogonal, then there is only one geodesic. If they are not orthogonal, if some vectors are coming closer together, we can somehow find more geodesic than just one. That was the idea. What I mean by geodesic, let me show this here. If you have two orthogonal projections, here I is the identity, of course, infinite dimensional. This is infinite dimensional identity. So let me take this special case. What would be the midpoint? Like in 2 by 2 matrices, this would be the midpoint. What would be the geodesic? Is a curve of this kind. And if you look a little bit at this, you will see, if you take such a curve, then you will see that the following formula is satisfied. The distance between 2 points on this curve is exactly by this formula. This is how you define geodesic, just with distances, because we don't have any structure of differentiability. Okay, we can define this, and if P and Q are orthogonal, then you have just one geodesic. If they come a little bit closer, then you have much more than just one geodesics. And that was the main step in the proof of this theorem. It's very geometrical proof. Okay, thanks a lot. That's all I wanted to say.
Okay, let us thank Professor Šemrl. And now questions, comments, please, to Professor Šemrl.
Yeah. Yes.
Questions, comments, please. Let me see, maybe there are some in chats. There are some thanks in chat, but I cannot see questions.
Yeah, it's I'm sorry. I mean, it was kind of linear algebra, so in some sense it's close to the main topic of your seminar. But I know I'm I'm not exactly in the mainstream of your.
No, it was very interesting. It's really very interesting. So that's just probably. What do you think the most interesting open questions, which
The most interesting
still open in this?
The most interesting,
on your opinion.
Okay, let me come back to the so this for me the most thank you very much. That is the most interesting question. I don't know, can it be obtained? I showed here how this all connected with Gleason's theorem, but I don't know how to use it here. So the Ulhorn's theorem, let me go to Ulhorn's theorem. Just a little bit more. It must be here, I guess. Ulhorn's theorem. I have a Hilbert space. Sorry, here I have to take infinite dimensional space. I have an infinite dimensional Hilbert space if I have a bijective map with a property that P and Q are orthogonal if and only if P and phi Q are orthogonal, then this is a standard map. Now the question that I was, and with some colleagues we were thinking about this, what if we have a map on projections of rank 1, which is bijective and preserves orthogonality, but not in both directions, just in one direction. So the assumption is you have a bijective map on P1H with a property. If P and Q are orthogonal, then phi P and phi Q are orthogonal. So here, instead of implication in both directions, you have just implication from this direction to this direction. And the conclusion, I would bet $100 to $1 that the same conclusion is true. This map has to be unitary, implement unitary or anti-unitary similarity. In the finite dimensional case, this is true even without bijectivity assumption. But in the infinite dimensional case, I don't know how to prove it. It looks like it's a very, very natural, very trivial question. You have, let me put it geometrically, you have a Hilbert space, infinite dimensional Hilbert space, you take all one-dimensional, you take the set of all one-dimensional subspaces, so the projective space. You have a map, bijective map, from one-dimensional subspaces onto one-dimensional subspaces. If two one-dimensional subspaces are orthogonal, then the same has to be true for the images. Prove that this map is implemented by unitary or anti-unitary operator. As far as I know, this is an open question, and I have no idea how to solve it. Very simple. I mean, formulation is very simple.
Nice. Yes, what's like, and you have very formulations all are very simple usually. Well understand. Yes, well understood.
Yeah, I guess I am.
Okay, really interesting question. Yes. Some more questions, please, comments. Okay, then let us thanks again Professor Šemrl for very interesting talk. Thank you very much.
Thanks. Thanks a lot for inviting me, and thanks a lot for listening to me in the morning, in the evening, in the night, in the lunchtime. Thank you.